Good morning everyone, my name is Jantuma Namrata. Today I will be presenting my project on the role of beta-actin in identifying new type of nuclear actin structure in U2OS cell named as funny. This study mainly focused on the expression of beta-actin as GFP fusion protein using a specific plasmid which will allow us to track its location and function. Beta-actin ACTB, this is the accession number, this is the sequence that we got from UDPort. This is highly conserved cytoskeleton protein that helps us to maintain cell shape, motility, and structural integrity. Beyond its classical role, cytoplasm, recently studies have shown that beta-actin plays an important role in nuclear function, including transcription regulation and chromatin remodeling, which makes it highly utilized for my study. After that, I have constructed my plasmid. This is my plasmid. For this is very utilized important because it has CMV promoter that ensures high level expression in mammalian cell. It also has this EGFP fusion that helps me to do real-time visualization of my beta-actin in live cell. It also has multiple cloning section, which makes it easier for me to insert my beta-actin. Amazingly, it also has kanamycin resistance gene, which will help me to do my antibiotic resistance study for the confirmation. For the primer design, I used two of my restoration enzyme, these two, and then for this, at first I inserted my first primer restoration enzyme XHOL, and then I inserted my ribosome binding site. This is mammalian cell, so I used COSEC sequence. This is my start codon in yellow. This is the sequence from my cDNA. After that, I designed my reverse primer. For this, I took a specific sequence and then I did reverse complement of the sequence, which had stop codon as well. So this is my restriction enzyme HIND3 for this, and this is my reverse complement sequence. After PCR amplification, I amplified my gene, and then to express it in my plasmid, I had to insert my gene. To do that, I used a similar restoration enzyme, this too, and it made a cut, made sticky end. Then I inserted my beta-actin gene through multiple cloning sequence, and here for the ligation I used T4 DNA ligase, which I made my expressive plasmid construction. I'm done with it, and here you can see C3. This indicates my gene will insert here, and after that my EGFP will be there for better visualization. After constructing my plasmid, I had to transform it in E. coli for replication and verification. In LV broth, my E. coli grew, and after that, through antibiotic resistance, I collected the colonies that successfully had my desired vector. For plasmid verification, I used mini-prep. After that, I could see the purity through agarose gel. For restriction enzyme, I used these two restriction enzyme to make a cut, and it will ensure, because it will only make the cut if my plasmid was inserted. Through Sanger sequencing, I used CMV forward primer of my vector, and then I did capillary electrophoresis. For visualization, chromatogram and blast was used. It helped me to identify if my sequence was good through a pick, and blast helped me to identify if there was any mutation, which wasn't. Then for the beta-actin GFP fusion in my mammalian cell U2OS, I had to use this liposuction with reagent, which was incubated for 24 to 28 hours. Through fluorescence microscopy and Western blotting, I successfully identified that it was inserted in my mammalian cell. Fluorescence microscopy helped me to identify the location and function of it, and through Western blotting using anti-GFP and anti-beta-actin antibodies, I could successfully say it was inserted. Which brings me to end of it. This is my reference, but I could understand that beta-actin GFP in my mammalian cell was inserted, and through that I could identify the nuclear actin structure and get the understanding of it, which is known as flanin filament. Thank you so much for your time. Have a great day.